Good day everyone. Today I will be discussing about the sampling distributions, the multiple sample case. What is sampling distribution? A sampling distribution is a probability distribution of a statistic obtained from a larger number of samples drawn from a specific population. The sampling distribution of a given population is the distribution of frequencies of a range of different outcomes that could possibly occur for a statistic of a population. In statistics, a population is the entire pool from which a statistical sample is drawn. A population may refer to an entire group of people, objects, events, and measurements. A population can thus be said to be aggregate observation of subjects grouped together by a common feature. So far, we have studied sampling distributions of statistics when we are sampling from only one population. Often we sample from more than one population. Sometimes we are interested in estimating difference in two population means or proportions, and sometimes we are interested in estimating the ratio of variances, for example, in these comparisons: the mean lifetimes of two comparable brands of batteries, mean downtimes at two different factory locations, proportion defectives produced by three different assembly lines, variation in resistance measurements for rubber made using two different coupling agents. In each of the above examples, we are interested in comparing parameters for two or more populations. To do so, we must take a random sample from each of the populations and compare the statistics computed from the samples. Let's take at the sampling distribution of the difference in sample means. So why do we care about the sampling distribution of the difference in sample means? The main reason is that the difference in sample means is the usual estimator of the difference in population means. And to construct the appropriate inference procedures for the difference in population means, we need to know the characteristics of the sampling distribution of its estimator. Yun yung difference in sample means. Let x1 bar represent the mean of n1 independent observations from a normally distributed population with mean mu1 and variance sigma 1 squared. Let x2 bar represent the mean of n2 independent observations from a normally distributed population with mu2 and variance sigma 2 squared. And we're also going to let here x1 bar and x2 bar be independent, which could be the case if we are sampling independently from the two different populations. So what is the mean of the sampling distribution of x1 bar minus x2 bar? Here, if we want the mean of the expectation of x1 bar minus x2 bar, this is simply equal to the expectation of x1 bar minus the expectation of x2 bar. We can split those up. The expectation of x1 bar is simply the mean of the population from which we are sampling. In other words, mu1 and similarly for mu2. So, on average, x1 bar minus x2 bar is equal to the difference in the population means. In other words, the difference in the sample means is an unbiased estimator of the difference in population means. What is the variance of x1 bar minus x2 bar? Here, if we want the variance of x1 bar minus x2 bar, we need to recall that if two random variables are independent, the variance of their difference is equal to the sum of their variances. And so if we have independent samples here, this is going to be equal to the variance of x1 bar plus the variance of x2 bar. And this is going to be sigma 1 squared over n1 plus sigma 2 squared over n2 over n2. So, ganito lang yung magiging variance kapag meron tayong dalawang independent samples. And complicated na siya kapag dependent naman yung samples. overall, what is the distribution of x1 bar minus x2 bar? The difference in sample means is going to have a mean equal to the difference in the population means, and the variance equal to the sum of the variances of x1 bar and x2 bar. The difference of x1 bar minus x2 bar will be normally distributed regardless of the sample size if we are sampling from normally distributed population. If we are sampling from populations that are not normal, the distribution will be approximately normal provided we have a large sample sizes. Let's take a look at the sampling distribution of the sample mean x bar. We will assume we are sampling from infinite populations, or that we are sampling only a small fraction of the finite population. Suppose we are sampling from a population with mean mu and standard deviation sigma. Let x bar be a random variable representing the sample mean of n independently drawn observations from this distribution. And a couple of the important points: the mean of the sampling distribution of the sample mean is equal to the population mean. Mu x bar is equal to mu. Symbolically, the mean of the sampling distribution of x bar is equal to the mean of the population from which we are sampling. And standard deviation of the sampling distribution of x bar is equal to sigma x bar equal sigma over the square root of n. If the population is normally distributed, when the sampling distribution of the sample mean x bar is also normal. For probability calculations, we will standardize in the usual way. Here, for a single value, if we have some random variable x, that is normally distributed, then when we are standardizing for a single value, we say that z is equal to x minus its mean over its standard deviation. But for the mean of n observations, when we are standardizing, we will do a similar things. Z is equal to the sample mean x bar minus its mean, which happens to be mu over the standard deviation of x bar. At this is simply x bar minus mu over sigma divided by square root of n. Let's look at the sampling distribution of the sample proportion p hat. Here is a quick example. In a random sample of 200 parts from manufacturing process, 18 had major manufacturing defects. Here, p hat is the sample proportion is 18 over 200, and then it is equal to 0.09. The p hat represents the population, the proportion of the individuals or objects and the sample that have a certain characteristics. In statistical inference scenarios, we use the sample proportion p hat, estimate the population proportion p. And to develop the proper inference procedures, we need to know the characteristics of the sampling distribution of p hat. I'm going to assume that we are sampling from an infinite population, or that we are sampling only a small fraction of a large population. That is typically the case in practice. The situation changes a little bit if we are sampling a larger fraction of a finite population. We can view the sample proportion p hat as x over n, where x is the random variable that represents the number of individuals in the sample with the characteristics of interest, and n is the total number of the individuals in the sample. In many cases, x is a binomial random variable with parameters n and p. So the sampling distribution of p hat is based on the binomial distribution. Like the binomial random variable x, the sample proportion p hat is the discrete random variable. When we draw a sample p hat, we will take on of 1 n plus 1 plus all values. The P takes on 1 of n plus 1 possible values. We have 0, 1 over n, 2 over n, up through 1. The probabilities of these values will correspond to the probabilities that the binomial random variable x takes on the values 0, 1, 2, up through n. Recall that the binomial random variable x, it has a mean of n times p, has a variance of n times p times 1 minus p, and to that central limit theorem is approximately normal distributed for large sample sizes. So we're going to use these characteristics to derive the characteristics of the sampling distribution of p hat. So what is the mean of the sampling distribution of p hat? The mean or expectation of p hat is the expectation of x over n. Recall that when we multiply a random variable by one constant, the expectation gets multiplied by that constant. So we can take this 1 over n out front, in front of the expectation, and we end up with this. And since the expectation of x is n times p, this is equal to 1 over n times p, which is simply equal to p. On average, the sample proportion equals the population proportion, and so we say that the sample proportion p hat is an unbiased estimator of the population proportion p. What is the variance of the sampling distribution of p hat? Here, the variance of p hat is equal to the variance of x over n. Recall that when we multiply a random variable by a constant, the variance gets multiplied by the square of that constant. So we can take 1 over n out front, but we need to square it. And we end up with this. 1 over n squared times variance of x, it is equal to 1 over n squared times n times p times 1 minus p. And we know that the variance of x is n times p times 1 minus p. So the variance of p hat is equal to p times 1 minus p over n. Here, the standard deviation of the sampling distribution of p hat is just the square root of that. The square root of p times 1 minus p over n. The sampling distribution of p hat is approximately normal if the sample size is large. This is once again the central limit theorem. But there is a bit of a complication. The sample size required to achieve approximately normal, approximately normally depends on the value of p. If p is close to 0.5, the sample size does not need to be very large. But if p is close to 0 or 1, a much larger sample size is required. So let's stop to give a simple all-encompassing rule for when a normal approximation is reasonable.